This is lab number 4 that we're going to do. I'm going to show you because we missed it. Some students will have missed this lab on Anzac Day. So I'm going to go over lab number 4 for you just to show you how it works. And for people who missed the lab on Wednesday the 25th of April, you can take your results from this film and then write up the lab from the results you see on this film. Now lab number 4 is about inductance, L. L is a symbol for inductance. Students always have difficulty saying what inductance is. Inductance as a concept is one that's quite hard to grasp. What it means, what inductance tells you, is how much magnetic field you get for a flow of current. Now in lab number 4 we're going to be dealing with this coil here. So see what's going to happen is current's going to go into this terminal, going to go around these coils and come out of here. So we've got current flowing in this coil. Now, as I've told you in the lecture, whenever current flows, you always get a magnetic field. There's going to be some magnetic field comes out of here, goes around, and then back in here again. Magnetic field flows around here. Now, inductance then tells you how much magnetic field you get for a given current. Now, this coil is quite big, and there are many turns, so we expect to see quite a high inductance value, because we're going to get quite a lot of magnetic flux for a given current. Remember, if we have many turns, for every turn of the wire, we're multiplying the flux. Now, in the pretest for the lab, let's just look at the answers to the pretest questions. The first question says, if the turns on a coil is doubled, what will happen to the inductance? Well, the answer to the question 1 is that it will go up by 4 times. Because the actual magnetic field increases as well as the turns increasing, which means the inductance goes up proportional to the square of the turns. So if I double the turns, I'm going to get 4 times the inductance. See, inductance tells you how magnetic a circuit is. A circuit with high inductance means it's a magnetic circuit with a strong magnetic field. And the more turns we have on the coil, the more inductance we get. So twice the turns is 4 times the inductance. Next thing it says, if the frequency changes, does the inductance change? And the answer to that question is no. Inductance depends upon purely the dimensions of the coil. It does not depend upon the level of current or the flux flowing in the coil. So the answer to question 2 is no. Inductance does not change with frequency. Question number 3 says, if the frequency increases, does the voltage across the coil rise or fall? Well, we haven't done that in class yet, but as we'll see later, when we have an AC supply, it creates a voltage across the coil. And the higher the frequency and the higher the current, the bigger the voltage across the coil. So the answer is, if the frequency increases, the voltage across the coil rises. So the inductance stays the same with frequency, but the voltage across the coil rises with an AC circuit. Now, next question says it's about mutual inductance. Mutual inductance is when we have one coil and another coil just beside it. And some of the magnetic field from one coil links with the second coil. When that happens, we have what's called mutual inductance. And question 3 says, if you bring the 2 coils closer together, does the mutual inductance rise or fall? Well, the answer is it rises. If I bring the 2 coils closer together, there's more magnetic field is going to link both windings, so the inductance goes up. Now, mutual inductance has the term M. It's almost the same as L, except for this. It's the flux in the second coil caused by current in the first coil. So, on this rig we've got 2 coils. There's a big coil on the inside and then a little coil here. That's coil number 1, coil number 2. And there will be mutual inductance between these 2 coils, because the current in the first coil will cause the magnetic field to flow inside the second coil, and therefore mutual inductance will exist. M equals phi2 of I1. The last question says, if a core material is changed from air to steel, what effect will that have on the inductance? Well, the answer is it will go up by a lot, so it will rise greatly. If I see, at the moment it's empty, there's nothing inside the coil. But if I fill that space with steel, then the magnetic field, this term here, the phi, will greatly increase. So that means that inductance will increase a lot if I put steel in here. Now let's look at page 21, which is the actual lab itself. Now the first thing you do in the lab itself is you work out the calculated value of the inductance of the big coil, coil number 1. And for that you need the formula that's on page 21. And the formula says the inductance is n squared times the area of the coil times mu. Now in this case mu naught, because it's a hollow coil, therefore it's just free space, divided by the length of the coil. Now for coil number 1, I can tell you what the numbers are. N is equal to 950. There are 950 turns on coil number 1. The diameter is 11 centimeters. That's A. So say D equals 11 cm. So to get the area, you've got to say area equals pi d squared over 4. And that's how you get the area in that equation. And finally, the length is 43 centimeters. So you've got to take that data of the dimensions of the coil, put it into that formula, and that will give you your calculated value of L. And later in the lab, you're going to compare your calculated value with your measured value. So in your logbook, I want you to calculate that out and see what you get. Alright, now let's have a look at the actual measurement of the coil. We've done the calculation, now let's measure it. Now to do this, what we're going to do is take a supply from the signal generator and we're going to pass it into coil number 1, and then the current will flow out from coil number 1 into a resistance, and the resistance we're going to use is 200. So the resistance box is set to 200. And finally, we go back to the earth on the signal generator. So do you see we set up a series circuit with R and L in series. It's going to be current flowing around this circuit from the supply, through the coil, through the resistance, back to ground. Now, what happens next is we're going to use the oscilloscope to measure the voltage across the resistance and also the voltage across the coil. And in this way we can figure out what L is. So remember, we always must be careful with an oscilloscope to put the earth in the right place. And the earth on the diagram goes here. Now V1 is the voltage across the coil. So channel 1, that's V1, that goes to the supply to the coil. And V2 goes to the resistor. And that's the circuit that's drawn on your experiment page. Now, we're going to use the scope to measure those two voltages. So let's get the scope going. And the generator's already going. We want to see 1 kilohertz, so 100 times 10, that's 1,000 hertz. And that will give us the voltage. And now on the oscilloscope, you see, we can see the two voltages. The voltage across the coil and the voltage across the resistance. Now the top one is the voltage across the coil. The bottom one is the voltage across the resistance. Now remember how we measure voltages from an oscilloscope. We must look at how many centimeters there are, and here it's about 2 centimeters peak to peak. Now 2 centimeters times the range on here, which I need my glasses to see, I think it's 1 volt, so that's about 2 volts. So the voltage across the resistance is 2 volts. And the voltage across the coil is about 3.5. 3.5 times, well, let's go to 1 volt per centimeter, that makes it easier. And that's about the same actually, which it should be. That's how I designed it to be. So we've got about 2 volts across the resistance and 2 volts across the coil. So those are the measurements that we've made. So now going back to the board, I can say that the circuit we've got is like this. We have a coil, and we have a resistance, and we've measured VR, which is voltage V2, and we've also measured VL, which is voltage V1. Now, we know that's 200 ohms, So we can find the current. We can say I equals VR over 200. So that's 2 over 200. And that's what you've got to do. You've got to work that out. And then you say that XL, which is like the ohms of the coil, is VL, which is also 2 volts in this case, divided by I. And finally, you say L equals XL divided by 2 times pi times the frequency, which is 1,000 hertz. Okay, so if you follow those steps through, you find you say 2 over 200 is your current, VL, which is V1, which is 2 volts as well, that is divided by the current will give you the XL, and finally L equals that. If you do this correctly, you'll find that the value you get from here and the value that you got from this equation come out almost exactly the same. This lab always works pretty well for us. And so that's how you check your calculated value and your measured value of L. Now the only other thing to do, which is essential for lab number 4, is a test of mutual inductance. Now for the mutual inductance test, it doesn't actually change that much. All we do is we, instead of looking at the voltage across coil number 1, the big coil, we take channel 1 and we put it across channel the second coil, coil number 2. And then again we take our readings. Now we haven't changed the resistance value, so we don't expect to see any change in that. And that's still going to be 2 volts. So it's 2 squares times 1, 2 volts. But we've got a different value now for the voltage across the second coil. This is VL2, you might say. And again it's 2 squares, but now it's 2 squares times, I think it's 0.1. So we've got 0.2 of a volt. So for the mutual part of our lab, we're going to say that VR is the same as before, 2 volts, but VM, or let's say VL2, the voltage across the second coil, is 0.2 volts. Now to work out your value of M, this is what you do. You say I1 equals 2 volts, again, across the resistance, divided by 200. This is before. And then you say that XM, this time the mutual reactance, is equal to V2, that's the voltage across the secondary coil, 0.2, divided by I1. And finally M equals XM, again divided by 2 pi times 1,000. And what we've done here is we've worked out the mutual inductance of the coil. So you've got to go through those steps and come up with a value for mutual inductance. Now mutual inductance is not the same as L. When we calculated this one, and these two match up fine, but that's all to do with the primary, the big, long coil with 950 turns. This bit of theory is to the secondary coil, which has far fewer turns. In fact, only 110 turns. And you get a value for M. M tells you how much of the flux from this first coil links with the second coil. That's what M is all about, mutual inductance. So, you've got to go through those calculations. Let's just recap once more. First, you calculate L1. That's the inductance of the primary coil. From that formula, using that data. Second, you use this data here. In your logbook, you write down these results. And you calculate the value of L using this method, knowing that VR equals 2 volts, and also, by design, the way I set it up, VL equals 2 volts. You understand, they don't have to be equal. I made them equal just for ease of using the scope. So those are your numbers, put them in there, and you get your measured value of L. And finally, you go to the mutual inductance part of our lab, which is what we see here. You work out M using this process. This time VR equals 2, VL2 equals 0.2 volts. Now, there's a couple of other things I want to say. In the lab, what it says is you must repeat this over and over again at higher frequencies. We can do that simply by increasing the frequency of the signal generator. Now, if you do that, what you'll find is that the low frequencies at 1 kilohertz and 10 kilohertz, you get pretty good results. Everything works fine. But at really high frequencies, it doesn't work. You'll find you get the wrong answer for the measured value of L. What that's telling us is that this equipment is fine at low frequencies. When the frequency is high, because of stray capacitance, we don't get good results. And if you want to measure the inductance at higher frequencies, you've got to think of another way of doing it. This way won't work. This way is fine if the frequency is low. It's not very good if the frequency is high. And finally, the very last thing I want to point out is that I hope that some of you, when you watch this film, have remembered that on the signal generator, one of the terminals is earthed. That one is earthed. And yet, when I wired up the experiment, I didn't put the earth on the earth terminal. Now that's very unusual. That's only ever going to apply in this particular lab. The thing is, I wanted to measure both V1, VR and VL, so I had to earth this point. If I put an earth here, I cannot have an earth there as well. That would short out the resistance. So that I got around that problem by using this thing. This is called an isolation transformer. And what that did was isolate the signal generator from ground. So even though it says earth on there, in fact in this particular case it's not earth. Just for this one lab, that point is not the earth point. And I've chosen to earth a different point in the experiment. I've chosen to earth this one here. That's a sort of a small point. But you should put that in your logbook. It's an important result. Well, it's an important thing you should have learned. Okay, so I want you to write down your answers to the pretest in the orange book, and then to do the work I've just described in your logbook. If you do all that, you can hand it in as part of your log report. It doesn't have to be signed because it's done from the film.